Hello friends, I am Professor Rajendra Baburao Gharse, working as a head of Electrical Engineering Department at NB Navle Sinhagad College of Engineering, Solapur. I am having a teaching experience of 9 years. I have completed BE Electrical from Government College of Engineering, Karad, and M.Tech from Indian Institute of Science, Bangalore. I have qualified GATE examination 6 times, and in the highest achievement, I have secured the All India 7th rank in the GATE examination with a percentile of 99.96. Okay, so today we are going to discuss about the three-phase inverters. Okay, so three-phase inverters. So let us discuss the circuitry of the three-phase inverters. Right. So here it is a three-phase inverter circuitry. Okay, it consists of 6 switches S1, S1, S2, S3, S4, S5 and S6, right? So we are having the total 6 switches. Be careful, the switch numbering are, it is like this. This is the first, this is the third, this one is the fifth, here it is the fourth, sixth and the second, right? We need to give the switch numbering like this only, right? Because if we change the switch numbers, then our operation table will change, right? We'll discuss what is the operation table later on. Okay, so please be careful. We need to assign the switch numbers like this only, 1 3 5, and next one is the 4 6 and 2. Be careful, it is not 2 4 6, it is a 4 6 and 2, 4 6 and 2. Input is a DC, as it is inverter, right? Inverter is a DC to AC converter, right? So definitely the input is a DC. Okay, next the load is 3-phase load. The load may be star connected or a delta connected. The load may be star connected or a delta connected, right? Across each switch the diodes are connected, D1, D3, D5, D4, D6 and D2, right? So but same as that of the single phase inverters, for the purely resistive load there is a no functioning of the diode. Okay, so diodes will be in the functioning, diodes will be functioning only when the load is inductive or the RL load. Okay, RL load. Next, the load is either star connected or a delta connected. Now in a 3-phase inverters, right, we are having 2 modes of operation. One is a 180-degree mode, second one is a 120-degree mode. In a 180-degree mode, each switch conducts for 180 degree, and in 120-degree mode, each switch conducts for 120 degree, right? Are you getting the point? So in 180-degree mode, each switch conducts for 180 degree, 120-degree mode, each switch conducts for 120 degree. Okay, so this is the difference. So we are going to discuss in 3-phase inverters 2 modes, basically 180-degree mode and the 120-degree mode. Let us first discuss the 180-degree mode. Okay, so 180-degree mode, as we know, in the 180-degree mode each switch conducts for 180 degree. Okay, so here it is the operation table of the 180-degree mode 3-phase inverter. Okay, we are having total 6 intervals, right? We are having total 6 intervals, 6, right? 1 to 6 intervals. Next, at a time in 180-degree mode, at a time 3 switches will be in the on state, right? That is the conducting devices, means 561 means it is a S5, S6 and S1 will be in the on state during first interval, right? During the second interval, S6, S1 means 6 and 1 as it is will remain here. Next, second switch number 2 will be adding, right? And which switch will be the outgoing switch before or at the end of first interval? It is a switch 5, right? It is a switch 5. Next, so for the third interval, 1 2 3 switches will be in the on state. For the fourth, 2 3 4. For the fifth, 3 4 5, and for the sixth it is a 4 5 6. Okay, so if we keep the switching like 1 3 5 4 6 2, then and only then this operation table will be valid, right? If we change the switch numbers there, then the operation table will be changing, right? Are you getting the point? So first S5, S6, S1, after that S6, S1, S2, after that 1 2 3, after that 2 3 4, 3 4 5 and 4 5 6. Okay, next here are the incoming devices and the outgoing devices, right? Incoming devices means what? Okay, so before the starting of this interval, right, which interval was there? That is the sixth interval. So operation will be like after one the second interval, after second the third, after third fourth, fourth fifth, after fifth sixth, and after sixth again it is a first interval. Each interval is of 60 degree. Okay, so 60 into 6, that is a total 360 degree. Total is a 360 degree. Are you getting the point? Okay, so 360 degree means one complete cycle of the. Okay, next, so before the first interval, which three switches will be in the on state? S4, S5, S6. Okay, so during this interval, which switch has added? That is the switch number 1. That is the switch number 1. Okay, so that's why the switch number 1 is the incoming switch. Okay, now which switch, right, which switch is not present in the first interval and that is present in the sixth interval? That is the switch number 5, right? So here S4 is the outgoing switch. S4 is the outgoing switch, right? Next, so as long as the operation is considered, these two columns are not important. These two columns are not important, but this important, right? Next, so 180 degree mode, at each switch conducts for 180 degree. So if you check here, switch number 1 is present, here switch number 1 is absent, right? Switch number 1 is present in the first interval, switch number 1 is present in the second interval, switch number 1 is present in the third interval also. Whether the switch number 1 is present in the fourth interval? No, right? So can we say switch number 1 is present in the 3 intervals, right? As I said, each interval is of 60 degree, right? So 60 into 3, that is a total 180 degree. So can we say that switch number 1 is on for 3 intervals, that is nothing but 180 degree. Similarly, check switch number 2. Switch number 2 is also on for 3 intervals, right? So 3 into 60 means 180 degree. Switch number 3 is also on for 3 intervals, right? So similarly, each switch will be in the conduction mode for 3 intervals. That is nothing but a 180 degree. That is nothing but a 180 degree. Okay, now, so for 180 degree mode, okay, now suppose if we go into market and if we purchase a 3-phase inverter, what are our expectations from the 3-phase inverter? Yes, the first thing is that inverter should give the balanced output, balanced supply, right? That is a balanced 3-phase output, right? It should be having a 3 sinusoidal waveforms, right? Second requirement is balanced means what? Yes, it should be having a 120 degree phase displacement between the each 3-phase voltages. Also, the RMS value or the maximum value of each phase voltage as well as the line voltage, it should be same, and the frequency of each line voltage or the phase voltage should be same. Are you getting the point, right? So the balanced supply means what? The phase displacement, mutual phase displacement should be 120 degree. The frequency of all the phase voltages or the line voltages should be same. The maximum value of all the phase voltages and the maximum value of all the line voltages should be same, right? And in addition to that, yes, what is the special requirement? The output of the inverter should be the sinusoidal one, right? Now let us check which type of output our inverter is giving, whether our inverter is giving a sinusoidal or not, whether our inverter is giving the balanced output or not, right? We are going to discuss. Okay, so here we are having the operation table. Next, so suppose for the first interval, so here we have considered the, suppose the load is the star connected and it is a purely resistive load. Okay, and so during the first interval, how will be the equivalent circuit? How will be the equivalent circuit? We are going to discuss, right? So during the first interval, switch number 5, 6 and 1 are in the on state, right? Switch number 5, switch number 6 and switch number 1 are in the on state, right? And we have considered the load is star connected and it is a purely resistive load, right? So we are having the load phases as A, B and C, right? And so it is a 3-phase star connected means what? Here we will be having a resistor and resistor. Are you getting the point? 3 resistors will be having. Okay, and during switch number 5, switch number 6 and switch number 1, these three switches are in the on state, right? So when switch number 1 is in the on state, right, can we say that the phase A, right, the phase A of the load will be connected through S1 to the positive plate of the EDC? Are you getting the point? Phase A of the load is connected through S1 to the positive plate of the EDC. Is this clear? Next, phase B of the load is connected through S6 to the negative plate of the EDC, right? So phase B is connected through S6. Why it is connected through S6? Because S6 is in the on state and S3 is open, right? So that's why phase B is connected to the negative plate of the EDC. What about the phase C? Phase C is connected through S5 to the positive plate of the EDC. Are you getting the point? So during the first interval, we are having the equivalent circuit such that, yes, the load consists of the 3 resistors connected in star. Out of that, the phase A is connected to the positive plate of the EDC. Phase C is also connected to the positive plate of the EDC, but phase B is connected to the negative plate of the EDC. So can we draw the equivalent circuit? Yes, we can draw the equivalent circuit. Phase A, so here we are having the star connected resistive load. Phase A and phase C are connected to the positive plate of the EDC and phase B is connected to the negative plate of the EDC. Are you getting the point, right? So we are having the equivalent circuit like this, right? Now here we are having the neutral point of the star connection, right? And here it is a phase A terminal, here it is a phase C terminal. So can we say that voltage across AN, that is a phase A and the neutral point, is nothing but the VAN, or it is represented with the EAN, right? That is a phase A voltage, VAN, right? Similarly, VCN, right, that is a voltage across the phase C or the phase C voltage, and VBN is the voltage across the phase B. So VAN is a voltage across phase A, VBN is a voltage across phase B, VCN is a voltage across phase C. Are you getting the point? Next, okay, so next, so again can we say that these two R and R are connected in parallel, these two resistors are connected in parallel, right? So R in parallel with is R by 2, yes. So further we can reduce this circuit as EDC R in parallel with R, this is replaced with R by 2, and I have represented A and C because A and C, these two terminals are shorted, right? So we have represented it as A comma C, we have represented it as A comma C. Are you getting the point? Next, so our task is to find the phase voltages, right? VAN and VBN as well as VCN. So here if you check, the current will flow in this circuit like this, because this is a positive plate, this is a negative plate, right? So as we know, current always flows from point of higher potential to the point of lower potential. So therefore here it is a plus, here it will be minus, because current in this resistor is in the downward direction. Current always flows from higher to lower. Similarly, current in this resistor is also from higher to lower. So that's why it is a plus here and minus here, right? Current is in the downward direction, so that's why it is a plus here and minus here. Next, so here can we say that by using the voltage division rule, R by 2 and R are connected in series, yes or no, right? Current in this current in the R by 2 resistor is in the downward direction. So can we say A is greater than the potential at terminal N? So VAN means what? VA minus VN, right? So can we say that if potential at terminal A, that is a VA, is greater than potential at terminal N, that is a VN, right? So VA is greater than VN means VAN will be positive, that is a VA minus VN is positive, right? Similarly, VC is greater than VN, right? So that's why VCN is also positive. So VAN is equal to VCN, okay? But if you check terminal N and terminal B, right? If you check terminal N and terminal B, so what will happen? Terminal N and terminal B, current is actually in the downward direction. We are having here it is plus, here it is minus. So terminal N potential is greater than terminal B potential. Very important. Terminal N potential is greater than terminal B potential, right? So VN is greater than VB. Okay, so what is a VB minus VN? That is a VBN. Whether it is a positive or negative, VB minus VN it will be negative because Vn is greater than Vb. Are you getting the point? Right? So Vnb is nothing but, by using the voltage division rule, we can find the Vnb. And what is Vbn? Vbn is minus of Vnb. Vbn is minus of Vnb, right? So by using the voltage division rule, yes, we can write Van is equal to Vcn, right? Because A and C are same, right? So Van is equal to Vcn. Van equal to Vcn is equal to total voltage is EDC into R by 2, that is the voltage across the resistor, divided by addition of the two resistors. So it is a EDC by 3. It is a positive. Be careful because current is in the downward direction. So therefore Va is greater than Vn as well as Vc is greater than Vn. Va is equal to Vc, right? So Van is equal to Vcn. Okay. So it is a EDC by 3. Similarly, can we find Vnb? Yes. Or Vbn is equal to minus of Vnb. Vbn is equal to minus of Vnb, which is equal to minus of, yes, R upon R plus R by 2 into EDC, that is minus 2 EDC by 3. Minus 2 EDC by 3. So very important. During the first interval, Van is equal to Vcn is EDC by 3. Vbn is equal to minus 2 by 3 into EDC. Minus 2 by 3 into EDC. So here, yes, here we need to draw the waveform. We need to draw the waveform for Van, Vbn and Vcn. Van or Ean, Vbn or Ebn and Vcn or Ecn. During the first interval, yes, as I said, each interval is of 60 degree. So it indicates first interval. This indicates the first interval. During the first interval, yes, what is the value of Van? It is a EDC by 3. It is a EDC by 3. Are you getting the point? This step, this pulse is EDC by 3. What is a Ecn? Ecn is also EDC by 3. What is a Ebn? It is a minus of 2 times EDC by 3. Minus 2 times EDC by 3. This is during the first interval, right? Similarly, during the second interval, yes, which two switches will be in the on state? 6, 1 and 2. 6, 1 and 2. Okay. 6, 1 and 2 are in the on state. So if 6, 1 and 2 are in the on state, 6, 1 and 2 are in the on state, switch number 6 is on, switch number 1 is also on, switch number 2 is also on, right? So if 6, 1 and 2 are in the on state, 6, 1 and 2 are in the on state, yes, can we say that phase A is connected to the positive plate of EDC, phase B is connected to the negative plate of EDC, and phase C is also connected to the negative plate of the EDC, right? Phase A, positive plate of the EDC, phase B, negative plate of the EDC, and phase C, yes, negative plate of the EDC, right? So phase B and C are connected to the negative plate of the EDC, and phase B and C are connected to the negative plate of the EDC, and phase A is connected to the positive plate of the EDC. So during the interval 2, yes, we have drawn the equivalent circuit. Yes, it is a EDC neutral point RRR. Phase A is connected to the positive plate of the EDC, phase B to the negative plate of the EDC, phase C to the negative plate of the EDC. Are you getting the difference between the first interval equivalent circuit and the second circuit equivalent circuit, second interval equivalent circuit, right? So here R and R are connected in parallel. So can we say that the voltage Vnb is equal to voltage Vnc, right? Are you getting the point? Okay. So again, these two are connected in parallel. So further, can we reduce it with R in parallel with R, that is a R by 2. Yes, so we have replaced it with a R by 2. So EDC, A, N, B, C and R by 2. B and C are connected together. So I have represented it with B. Next, by using the voltage division rule, right, we can find Van. Van is equal to R upon R plus R by 2 into EDC. Okay, Van is positive, be careful, right? Van is positive because current will flow like this. So it is a higher, this one is higher, this one is lower, right? Similarly, next N to B, this is a higher, this one is lower, right? Current downward direction. So that's why Vn is positive compared to that of the, yes, VB or VC. Okay, so VNB and VNC are positive, but VBN and VCN, those two will be negative, right? So by using the voltage division rule, we can find the values, we can find the values of VAN, VBN and VCN, right? VAN, VBN and VCN, right? So what is VAN during the second interval? It is 2 EDC by 3, and VBN, VCN is equal to minus EDC by 3, right? So VAN is 2 EDC by 3 and VCN is on VBN is minus EDC by 3. So here during the second interval means what? Yes, second interval means what? It indicates the second interval. This is a second interval, right? Getting okay. What is VAN by 3, right? What is the value of VBN? It is a minus EDC by 3. What is the value of VCN? It is also minus EDC by 3. Similarly, for each interval, yes, we can draw the equivalent circuit, right? Depending on the, we need to check the operation table. After that, we need to check which switches will be in the on state. After that, we need to decide where the phase A is connected, where the phase B is connected, where the phase C is connected, right? After that, we need to draw the equivalent circuit, yes. And after drawing the equivalent circuit by using the network theory, we need to find the value of VAN, VBN, VCN, and we need to draw the circuitry. We need to draw the circuitry, right? So here from here to here, that is 2 pi, right? From t is equal to 0 to, sorry, omega t is equal to 0 to omega t is equal to 2 pi. We are having one complete cycle, okay? Yes, 0 to 2 pi, we are having one complete cycle. 0 to 2 pi, we are having one complete cycle, okay? Now please check what is the, whether it is a sinusoidal? No, it is a stepped waveform, right? It is a stepped waveform. Next, what is the phase reference between VAN and VBN? Yes, check VAN after omega t is equal to 0. After omega t is equal to 0, we are having VAN is positive, right? It is having a EDC by 3, 2 EDC by 3 and again EDC by 3, this type of sequence, right? If you check, this type of sequence is repeating in VBN, yes, that is after this interval. It is a EDC by 3, 2 EDC by 3 and again EDC by 3. Okay, so can we say that VBN is lagging to VAN by 2 intervals, right? By 2 intervals. So these 2 intervals means after 2 intervals we are having the same waveform for VBN as that of the VAN, okay? So VBN is lagging to VAN by 2 intervals. 2 intervals means how much degree? It is a 2 into 60 degree because each interval is of 60 degree. So it is 2 into 60, that is a 120 degree. Are you getting the point, right? Similarly, check for VCN. Check for VCN. So if you check EBN, we are having waveform like minus 2 EDC by 3, minus EDC by 3 and plus EDC by 3, right? So if you check the VCN, we are having minus 2 EDC by 3, minus EDC by 3, plus EDC by 3, right? So whatever the waveform we are having for VBN, that waveform is appearing in VCN after 2 intervals, right? Means after these 2 intervals we are having the waveform of EBN which will be appearing in the VCN, right? So can we say that VCN is lagging to VBN by 120 degree? Are you getting the point, right? So the mutual phase displacement between VAN, VBN, VCN, it is a 120 degree. Are you getting the point? Similarly, check the peak value of each phase voltage. Yes, here the peak value is EDC by 3. In this VBN, the peak value is again EDC by 3, right? Sorry, 2 EDC by 3. Here it is 2 EDC by 3. Here it is also 2 EDC by 3. Each step is of EDC by 3, right? So that's why it is, we are having 2 steps, so it is a 2 EDC by 3. What is the peak value of VCN or ECN? It is also 2 steps, so that's why it is a 2 EDC by 3. It is a 2 EDC by 3. Are you getting the point? So these are the waveforms for phase voltages. Similarly, can we draw the waveforms for line voltages? Yes, line voltage means VAB, VBC and VCA. How to draw the waveform for VAB? Yes, VAB is equal to VAN minus VBN or EAN minus EBN, okay? So VAB is nothing but interval by interval subtraction between these 2 waveforms, that is EBN and EAN, right? So can we write during the first interval? During the first interval, yes, what is the value of EAN? It is a EDC by 3. What is the value of EBN? It is the 2 EDC by 3. So if you take the subtraction, yes, it is like EDC by 3 minus 2 EDC by 3. So EDC by 3 minus of 2 EDC by 3 means what? EDC by 3 minus of minus means what? It is plus. So EDC by 3 plus 2 EDC by 3. So it is EDC. Are you getting the point? EDC by 3 plus 2 EDC by 3 is nothing but a EDC. During the second interval, if you check EAN minus EBN, yes, it is 2 EDC by 3, 2 EDC by 3, yes, minus of minus EDC by 3. So 2 EDC by 3 minus of minus EDC by 3 means what? 2 EDC by 3 plus EDC by 3. So it is again EDC. During the third interval, yes, it is EDC by 3 and this is also EDC by 3. So if you take the subtraction, EDC by 3 minus EDC by 3, it will be 0, right? So during the third interval, it is having a waveform having a EAB value is 0. Are you getting the point? Right? Similarly, we can find it for remaining intervals. How to find VBN or VBC or EBC? VBC is or EBC is equal to VBN minus VCN, and similarly VCA is nothing but VCN minus VAN. Are you getting the point? So we need to take the interval by interval the subtraction between the phase voltages, right? So by using this or by doing the subtraction between the respective phase voltages, we can draw the waveform for line voltages. We can draw the waveform for line voltages. Be careful, in 180-degree conduction mode, the nature of phase voltages, in 180-degree conduction mode, the nature of phase voltages is stepped waveform. The nature of line voltages is, yes, nature of line voltage is, it is a quasi square, because it is a having a non-zero pulse, 0, again negative non-zero pulse, again 0, again positive pulse, again 0, again negative pulse, right? So that's why it is a quasi square wave, right? Quasi square wave. Are you getting the point? Okay. Similarly, what is a phase displacement between the EAB and EBC? Yes, if you check after omega t is equal to 0, EAB is having a EDC and EDC up again 0. So we are having the sequence pattern like plus EDC 0, right? The same sequence is repeating in EBC after 2 intervals. Check here, plus EDC 0, right? So can we say that EBC is lagging to EAB by angle 120 degree, right? Similarly, we can check for ECA also, right? So phase displacement between the line voltages is also 120 degree. What is the peak value of EAB? EDC. What is the peak value of EBC? It is also EDC. What is the peak value of ECA? It is also EDC. It is also EDC. Are you getting the point, right? So we can say that we are having the fitly balanced waveforms, because all the line voltages are having the same peak value, all the phase voltages are also having the same peak value, right? The only thing is they are non-sinusoidal. They are non-sinusoidal, right? Next, as the output is AC, what is the effective value in AC circuit? Yes, it is a RMS value. Okay, so can we derive the expression for RMS value of phase voltage? Yes, RMS value of phase voltage, that is a VAN RMS or EAN RMS. Yes, so check the phase voltage waveform. Check the phase voltage waveform. Yes, whatever waveform we are having, omega t is equal to 0 to omega t is equal to 2 pi, right? The same waveform is repeating from 2 pi to 4 pi, right? So what is the periodic angle? It is a 2 pi. So can we write it as 1 by 2 pi integration? How many intervals we need to take? We need to take 0 to pi by 3 to 2 pi by 3 to pi to 4 pi by 3 and so on. Okay, so we are having total 6 intervals. So we can write it as RMS value, it is equal to 1 by 2 pi integration from 0 to 2 pi VAN square d omega t to the power 1 by 2. So square root of mean of squared value. Okay, so it is, yes, 2 pi integration from 0 to pi by 3 EDC square by 9, right? Because we need to take the square of the VAN. So during the first interval, it is a EDC by 3, so it is a EDC square by 9 d omega t plus pi by 3 to 2 pi by 3, and we need to put it the values of VAN, and after simplifying, yes, we can write VAN is equal to root EDC by 3. So what is the load power? Yes, load power is equal to, the load is 3 phase, right? So it is like we need to find the power of each phase and we need to multiply it with 3 because load is balanced load, right? In each phase we were having a load resistance of R, right? R ohm. So what is the per phase power? Is R phase voltage square divided by R, that is a V square by R. Okay, so VAN RMS square divided by R into 3 because we are having a 3 phases. Okay, so similarly after putting the value of VAN RMS, right, we can simply write it as VA load power is equal to 2 EDC square by 3R, 2 EDC square by 3R. Okay, so this is about the 3-phase inverter 180-degree conduction mode, right? So please be careful. As long as the university examination is considered, the important thing is they may ask you the question, write the circuit for 3-phase inverter with 180-degree conduction mode, right, and derive the expression for load power. Okay, so you need to write the circuitry, you need to write the operation table, as well as you need to draw the waveform, and after that you need to derive the expression of VAN RMS as well as the load power, right? Operation table is very important, circuit diagram is also very important. The important thing is the switch numbers in the circuit diagram. Okay, so this is about the 180-degree conduction mode 3-phase inverter. In my next video we will discuss about the 120-degree conduction mode, right, for 3-phase inverter. Thank you, thanks for watching.